So hello, this whiteboard seminar is going to give you an introduction to systems ecology. Systems ecology is essentially ecology with a systems thinking foundation or perspective. And systems thinking is a broad set of scientific disciplines or approaches that have the belief that understanding the parts or components of a system is done best by looking at the relationships between them and other systems rather than taking these components in isolation. So systems ecology is in essence a holistic perspective. Systems ecologists focus on the interacting components and parts to understand the aggregate whole, the ecosystem. And holistic perspectives are in stark contrast to reductionist scientific approaches, which try and understand complex systems by picking out the different individual components and studying them in isolation. And I usually use a very simple example to illustrate the strengths of holistic perspectives in comparison to reductionist approaches. So a phenomenon we might be interested in understanding could be termite hills. And intuitively, what you would like to look at to understand a termite hill is the termite colony itself. So these are some beautifully drawn termites. The reductionist would suggest that remove a single termite in isolation and study that, and you would get insights into how this termite hill is formed. And that's not really the case. To understand how the termite hill is created, how it's formed, you'd have to look at the whole termite colony and how they interact with one another to create this magnificent structure. So it's quite difficult often to pinpoint the exact moment in time in which a scientific discipline is introduced to the scientific community. Usually these things are a gradual evolution of ideas. But when it comes to systems ecology, 1960 is a good place to start, because it was then Howard Odum, who was an ecologist but a great systems thinker as well, was inspired to make analogies between ecosystems and other system types, such as heat engines or electrical circuits. And Howard Odum had the vision that ecologists should be studying the aggregate level of natural systems, ecosystems themselves, and not focus so much on the individual species in isolation. And by looking at this aggregate level, ecosystem level, ecologists would be able to make these predictions and generalizations about the system. And Howard Odum created these energy flow diagrams, which is actually the first applications of systems ecology in ecology. And what Howard Odum did was actually look at the flow of energy through an ecosystem. So he identified different components in the system. The external source of energy, the sun. Energy would flow into primary producers, which would get eaten by herbivores, different grazing animals such as mice. That in their turn would be eaten by a higher level carnivore, such as a weasel, which would be eaten by top predators such as an eagle. And this kind of visual picture gives us an indication of what systems ecology is all about and what systems ecologists are interested in. Systems ecologists define the boundary of a system, and this is an artificial boundary. We artificially decide what's inside a system and what's outside a system. And systems ecologists are interested in the different components of the system, the different species, the different organisms, which are very importantly interacting with one another. This is an important component of systems ecology, to understand the functional, structural relationships of these different components with each other in the aggregate whole. And so systems ecology has moved on beyond just mapping out the flows of energy within an ecosystem, and has given us some important insights in these complex aggregate behaviors of ecosystems, such as regime shifts, or these complex properties of ecosystems, such as resilience. regime shifts are these sudden and often quite dramatic shifts in the configuration of an ecosystem at the aggregate level. Which can be visualized by this ball and cup model. So the ecosystem changes or shifts configuration or state when it jumps from one cup to another cup. And some classic examples of these regime shifts are shifts from a live coral-dominated coral reef to coral reef dominated by these fleshy seaweeds, macroalgae. Or, for example, a healthy pelagic ecosystem dominated by top predators and mesopredators, a healthy food web, to a situation where jellyfish are the dominant species. So these large-scale ecosystem changes are difficult to understand and predict and know anything about if you just focus on single individual species, single individual components of the system. You have to take a holistic systems approach to do anything worthwhile to promote understanding of these phenomena. Now, resilience is the capacity of an ecosystem to withstand changes or disturbance before undergoing a regime shift, to avoid undergoing a regime shift. And systems ecology has given us some insights into what components of the ecosystem are important in providing resilience. For example, systems ecologists looking at the interactions of different organisms with each other have understood that different species, different organisms in the system have different functions, they do different things. And some of these functions are critical to uphold resilience in the system. For example, in the case of a coral reef, some fish species are herbivores. They eat macroalgae. That's their function. If you remove these from the system, the function of herbivory will be lost, and you're going to make the system more likely to undergo a regime shift to an undesirable macroalgal regime. In the same sense, by expanding the perspective and not just looking at interactions between species in a certain ecosystem, by looking at interactions between different ecosystem types within a broad seascape or landscape. For example, interactions between mangroves and seagrass and coral reefs has given us understanding that connectivity between these different habitat types and between different ecosystem types also provides insurance in the face of change and also provides resilience. So in summary, systems ecology has given us some critical, important insights in understanding how complex aggregate behaviors of ecosystems and properties of ecosystems function in an ever-changing world.